Hi, everyone. Thank you for joining this talk. My name is Amila, and I am a software engineer here with LexisNexis Risk Solutions. And it is my pleasure to introduce you to PyHPCC, a technology that combines the forces of Python and HPCC systems together. Before we jump into PyHPCC, let's time travel back to ancient Greece. Ancient Greece was a civilization with a network of interconnected cities. The Greeks had established routes that allowed the flow of information and goods from one city to another. So when major events would occur, the norm was to deliver messages or information through messengers who were also trained runners. These runners would carry messages from city to city using these specified routes. Now, the reason they used runners during battles to deliver messages was because other modes of transportation like horses were obviously sent off to battle. These runners, in fact, would dedicate their lives to ensure that messages would get delivered to the people on the other end. And this is because even in those days, information was deemed important. So Greece is a classic example of a communications network that facilitated communications via agents, in this case, runners, using these specified routes. In 490 BC, after the Greeks had defeated the Persians in the Battle of Marathon, Pheidippides, who was a trained runner, was thrilled to deliver the message of victory to his people in Athens. So he ran an arduous journey of 26 miles through rocky mountains and difficult terrain to deliver this good news to his people in Athens. As a fun fact, Pheidippides was the first to run a marathon, but unfortunately, it was his last run because after reaching Athens and delivering the good news to his people, he collapsed out of exhaustion. It goes on to show the dedication that these ancient Greeks placed on the value the ancient Greeks placed on the flow of information from one end to another. The word marathon was then coined after Pheidippides' last run from the Battle of Marathon. Since the time of Pheidippides, communications from point A to point B has tremendously evolved. We are probably as swift as the Greek god Hermes in delivering messages, if not faster. But we have our own versions of rocky mountains and difficult terrain that we need to overcome within our existing communication systems. The world today is translating most of its processes into automation or automated systems. Now, when we think of automation, we typically picture a robot that is diligently doing tasks and speaking to us in a monotone, which reminds me of a joke that is itching to come out, so I will yield to my temptation. So it goes like this. Once upon a time, there were three people. One was an inquisitive questioner, the second was a hardware engineer, and the third was a software engineer. So the questioner asks these two engineers, how many software engineers do you need to change a light bulb? To which the hardware engineer proudly replies, none, because it's a hardware problem. So the questioner looks to the software engineer for a response. The software engineer, however, looks confused at the question, and after a moment replies, well, the light bulb on my machine works just fine. So automation in the software world typically looks different. In general, it involves finding patterns within a process and translating those patterns into code. And this requires reliable communication between various pieces of technology within our automated system. And that's how PyHPCC was born. PyHPCC was born out of a need to establish reliable communication between two pieces of technology that we were using at that time. So on one end, we had Python, which was the language of our automated framework. And on the other hand, we had HPCC Systems, which gave us access to big data. Now, a team realized that Python by nature was not able to communicate with HPCC systems. You can think of it like a language barrier. So what our team did was to establish a bridge between the two disjointed pieces of technology. So in this case, PyHPCC was our bridge. In more technically speaking, PyHPCC is a Python package or a wrapper that is built around the HPCC systems web services that facilitates the communication between Python and HPCC systems. So let's delve into PyHPCC and how we can get started with PyHPCC. So the first thing is the setup. There are two prerequisites that we need to fulfill to get set up with PyHPCC. The first is Python 3, and the second is a version of ECL client tools that is greater than 6.x. And then once you have those prerequisites fulfilled, then you can simply open a terminal on your machine and then run this command that you see on the screen, which is pip install PyHPCC with the appropriate version of PyHPCC that you want to install. And then PyHPCC will be available for use. So a very easy and simple setup that we have built around PyHPCC. So let's go further in depth by exploring the functionalities that PyHPCC offers. Now, in the upcoming slides, I will only discuss 3 PyHPCC functionalities, but by no means is this an exhaustive list of the functionalities that PyHPCC offers. Let's start with authentication. Now, authentication by itself is not a functionality that PyHPCC offers. You can think of it as a sub-feature that is required by all the other PyHPCC functionalities that need to interact with the HPCC systems. So this is a prerequisite of some sort. So on the screen here in this code snippet, at first, we import the necessary modules. So in this case, we would import the authentication and the API modules. That's for the authentication piece. And then we would go through a bunch of configurations. So the first is specifying the necessary HPCC environment. So this would be the URL or the domain name of the environment or the HPCC environment that you're connecting to. And then along with the URL that you would use when connecting to an HPCC environment, you would also have a port associated, right? So you would specify the port in this case, and then you would specify the ECL credentials that you would use to log into HPCC systems. Now, in this case, I have placed all the values of my configurations within environment variables. You can choose to do the same too, so that you mask some of the sensitive information within your code. And then you specify the protocol that you connect to HPCC over. In this case, I am connecting to HPCC systems using the secure HTTP protocol. And then we go into creating the authentication object and the HPCC object. So we just simply pass in the configurations that we had set up on the top here, we pass in the environment port, the credentials, and the protocol into the authentication class, and then we receive an authentication object. So this is not where the authentication actually happens. This is just creating an authentication object for you so that you can use this authentication object with your PyHPCC functionality later on in your code. And then once you have the authentication object, then you go ahead and create an HPCC object. So what the HPCC class would do for you is it gives you access into several of these other PyHPCC functionalities. And that will help you access the methods associated with these PyHPCC functionalities, such as work unit submission or reading a logical file, which we'll go through in the upcoming slides. So the first functionality that I want to go over is a basic work unit submission. So on the screen here, these lines of code will look familiar to you from the previous slide, where we do the imports and then we also do the pre-configurations. So in addition to the imports that you had seen earlier, we also have an extra import, which gives us access to the work unit submission functionality. So this PyHPCC.workunit_submit gives you access to the work unit submission functionalities. And then in addition to those pre-configurations that you had set for authentication, you also have some more necessary configurations that you would need to do. So these are the configurations are clusters. So you can specify 2 clusters, and I'll get to that in a bit, why we specify or declare 2 clusters as our configuration. And then an inline ECL query. So this is just a simple output of a hello world string. And you save that in an ECL query variable. And then you give an appropriate job name for your work unit. And then also specify a working folder. So in this case, I specified the current working directory as my working folder, but you can feel free to point your working folder to any path on your machine. So the working folder is essentially the place where PyHPCC drops any kind of metadata that is generated during its executions, or any kind of compiled files that are generated when the code is executed. So then once again, after you declare the working folder, then you create the authentication and the HPCC objects. And then you pass that HPCC object into the work unit submit class that you had initialized or imported earlier on. And then also pass the 2 clusters. Now, for the basic work unit submission, or for work unit submissions in general, there are 3 steps that you need to follow. The first is to create a ECL file. So remember, we had an inline query in the beginning. So the first step required is to convert that inline query into a ECL file. And that's exactly what we are doing here when we pass in the ECL query, a job name, and the working folder. So once you execute this line of code, then it will create a .ecl file for you in your current working folder, or whichever working folder that you had specified. And the name of the ECL file will be the job name that you had specified earlier. So this ECL file name will be stored in this variable, which you will then pass into the second step, which is the compilation phase. And you would execute the bash compile method on that file name. You can also specify a Git repository, but in an upcoming slide, I will go more into depth on how you can do, or you can specify a Git repository during compilation phase. So once you run this or execute this bash compile command, then this command will generate two extra files for you, an ECL XML file and an ECL XML.xml file. So this ECL XML file is what will be stored in the output file variable. And the output variable will contain any kind of warnings or error messages that were generated during the compilation phase. So then we look for an error. So if there are any errors generated during this compilation phase, which is again stored in the output variable, we look for any kind of error messages. If there are no errors, then we proceed into submitting the work unit onto the HPCC system clusters. So bash run does exactly that. Bash run is where you submit, and this is also where the authentication happens with HPCC systems. And remember the time when I told you about the two clusters that we specify here? When you submit bash run, what PyHPCC will intelligently do behind the scenes is it will look at the activity on these two clusters, and it will schedule your work unit on the cluster with the least activity. So that is a nice, I guess, feature that PyHPCC offers. That is scheduling your work unit on a cluster with least activity. So once you complete or submit the work unit, then you will receive either an error and some kind of output. And again, when you run a work unit on HPCC systems, that generates a work unit ID for you. So if your work unit does take some time to execute, PyHPCC also offers a feature where you can wait until your work unit completes execution so that you can know whether your execution was successful or not. So the WU wait complete method allows you to wait for the work unit to complete so that either you can look for a success indicator, success or failure indicator, or you can also wait so that in the rest of the code, you can do some more analysis of the results that come out of your work unit. So right now, we just wait, but we simply exit just for simplicity's sake. But you can feel free to add to the functionality of this code snippet. Let's take a look at the results of the basic work unit submission. So over here, you can see that this is the HPCC systems interface, and I have a work unit that got submitted with a work unit ID and a job name, as you had seen in the code snippet, where I had named my job name as basic job submission. And then you can see that it chose the HTHOR dev cluster out of those two clusters that I'd specified. And this work unit has successfully completed running. And then if I go into the outputs tab, I see the hello world message, which was the output from that inline query that I had defined earlier. So that was the basic work unit submission functionality. Now, a variation of the work unit submission functionality is using a Git repository. So we begin with, again, the imports and the pre-configurations for authentication. And then we define two clusters that we would like to use during the work unit submission. And then we give an appropriate job name and also specify a working folder, just like we did in the previous example. Then we also have the option to specify a Git repository. In this case, I am specifying my Git repository as the current working directory, but you can also feel free to point your path to a different folder or a different path on your machine. And then in this case, I'm not using an inline ECL query. I'm actually storing my ECL query within a text file and reading the ECL query from that text file. Most of the work that we do with ECL are not one-line codes. Uh, and requires more involved pieces of queries that that even reference other modules within a Git repository. So because of that, I placed my snippet of code within a text file, and I'm reading the ECL query from this text file and storing it in a variable called ECL query. And then I do the or create the authentication and the HPCC objects, and then use or pass that HPCC objects like I had done earlier into the work unit submit class along with the two clusters. And then I go through the same 3 steps of creating an ECL file, bash compile, and bash run. So the place where I want to focus on here is the bash compile method, where I am able to also specify the Git repository that the compiler can use in order to successfully compile this ECL file that, or the ECL query that we want to compile. So when we specify a Git repository, it's not just your ECL query that is compiled, it's your entire Git repository references are also compiled along with it. So that will give you a set of warnings and errors if there are any. And then once you have that ECL XML file generated from a successful compilation from the bash compile method, then you can go into submitting the work unit just like we did earlier. And then you can wait for the work unit to complete its execution and then perform any other kinds of deeper analysis on that work unit, or you can simply exit like I'm doing here. So then the results are pretty similar to what we have seen earlier because it's just submitting a work unit. But in this case, it was using the Git repository. So you don't see anything visual on HPCC systems, but it just, it translates the work unit in terms of submission. So the cluster use again here is the HTOR staging. It shows one of the least one of the clusters with the least activity on it, and then submitted the work unit for you on that cluster. And then on the outputs, I just simply had a string which just said work unit submission using a file from a Git repository. So that was work unit submission using a Git repository. Now, the second functionality that I want to walk over is reading logical files. So after you have done your imports and created your pre-configurations for authentication, then you would want to specify which logical file you want to read from. So in this case, I have given a logical file name as such. And then you can also specify how many rows within the logical file you want to read from that particular logical file. So for example, if you have 1 million rows within your logical file, then and you only want to read just 100 rows, then you can specify here saying that I only want 100 rows to read from this particular logical file. If you set this number of rows to return as 0, then it will return the entire amount of rows. So if there are 1 million rows, it will return 1 million rows for you. Again, we do again the authentication or create the authentication object and the HPCC object. And then once you have the HPCC object, you can use that to access the get file info method, which does the reading of logical files from HPCC systems. And you provide the logical file name and the number of return or rows that you want to read from that logical file. So when you execute just this portion of the code, it will return a blob of a response, which is in fact a nightmare to parse through. So because of that, I just JSONify the response that comes through. That way it's a little bit more easier to handle within the code. So if you see here in the next line from the response, because I have JSONified the response, I am able to use this chain notation in order to access a specific result within that response. And then you can further make your response easier to access by using pandas, which is a data access library. It puts your JSON into a tabular format so that you can access it kind of like how you would access a Excel worksheet. So pandas translation here is happening, and then I just do a print of that pandas data frame. Nothing fancy, just a very simple snippet of code where I just read a file and then just output it to the console. So you can see here that my pandas data frame got output onto the console, and it is in a tabular format. And what was returned was a file position and a count of 9,095 records. Now, uploading files to a landing zone. This is a third functionality that I want to walk over with you. Again, we do the imports and the pre-configurations that are required for authentication. And then in addition to those pre-configurations, you have some more configurations that you would need to set up in order to upload a file to the landing zone. The first is the file path. So this is the path in your or on your local machine, which points to the specific file that you want to upload to the landing zone. And then you can give a specific file name. So you can, this file name doesn't have to be the same as your file which exists on your local machine. If you're unhappy with the file name on your local machine, you can definitely change it over here. And the file that gets uploaded onto the landing zone will have this file name that you provide in the code. And then you specify the HPCC landing zone IP address. Now, the only thing you have to be careful here is that you need to distinguish between a landing zone IP address and the HPCC environment IP address. They are different. So you want to provide the landing zone IP address in this case. And then you provide the landing zone path. So the landing zone path is the path on the landing zone where you want to upload the file to. So if you think of a landing zone as like Google Drive, for instance, you want to provide the folder path to the folder where you want to upload a specific file to. And then you create, again, the authentication object and the HPCC object. And then once you have that HPCC object created, before that, you would need to open your file that you're reading. In this case, I'm reading a text file, and read it as a byte file. And once you have it read as a byte file, you pass the file name that you have specified earlier on, along with the byte file that you have just opened. And you also specify the specific type of the file. So in this case, since I'm using a text file, I'm using text plain as my type. But if you're using some other kind of file type, like for example, a CSV, you would use the appropriate kind of type for that particular file. And you wrap this all around or you set this all as a tuple, and then you pass this information into a payload. So payload is kind of like an envelope with all the information that you need put into that envelope so that it is easier to seal and send within the request. So that is what a payload is. So in this case, I'm specifying that my payload has a net address of the IP address of the landing zone, and then the landing zone path, which I have mentioned up here, and then the file to upload, which contains the file name and the byte file that I've read along with its type. And once you have this envelope or the payload created, then you simply pass it into the upload file method that you can access using the HPCC object. So once you pass in that envelope or the payload into the upload file method, the upload file behind the scenes unwraps the payload and then uses the information as it needs to in order to handle the request. And then again, I JSONify the response that comes out of this upload file transaction that I do with HPCC Systems. And then once I have JSONified the response, I am able to access the result using the chained notation. So if the file upload was a success, then I'm able to print out onto the console saying that the file was uploaded successfully. Otherwise, if there was some kind of an error or exception that occurs, then I can simply print out that the file upload was unsuccessful. So here's the results of the upload or the code that we had for the uploading files to the landing zone. As you can see on my Python terminal, I have a file uploaded successful. And indeed on HPCC Systems on the landing zone, I have the text file uploaded along with the file name. And you can see the size of the file as well as the date timestamp. So those were the functionalities. And now I want to address the question, why use PyHPCC? Well, for one, Python is prevalent within the industry, and that makes it one of the commonly found languages within a programmer's toolkit. And compared to other programming languages, Python is relatively easier to learn. With the automated system that our team had developed, our team realized that Python's versatility makes it an automation-friendly language. Now, the use of PyHPCC within our team did not stop with automation. In fact, it extended out into other projects like some of our data science projects. Now, the data scientists on our team were very familiar with Python because they used Python machine learning libraries like scikit-learn or PyTorch for the work that they do. And the work that they do involved running tests on data within HPCC systems and then using the results from that test run within their analysis and visualization. So in the past, what would happen was that these data scientists would have to collaborate with an ECL engineer to run those tests on HPCC systems. But with the introduction of PyHPCC to our team, our data scientists were able to access HPCC systems using PyHPCC. So it gives them more accessibility to HPCC systems. Now, HPCC systems, by no doubt, is a powerful technology. And to communicate with HPCC systems, you need to know ECL, which is its programming language. But ECL as a language has a steep learning curve associated with it. So for newcomers to LexisNexis, beginners to HPCC systems, or even for technologists like our data scientists, PyHPCC is an alternative. It helps them temporarily bypass the complexities of learning a new language and rather focus on the work at hand. So again, PyHPCC is not a replacement to ECL. It just adds value when learning or by reducing the steepness of the learning curve associated with learning ECL and directly allowing the user to become familiar with HPCC systems. You know, when our team built out the PyHPCC package, they implemented 20% of the functionality that was on HPCC systems that was being used 80% of the time by its users. So the functionalities that just like we had looked at, like working at submission or reading logical files, only those functionalities that were used 80% of the time by the users were implemented into PyHPCC, which gives us room for collaboration. So if you are interested in collaborating and contributing to PyHPCC, feel free to reach us out at innovation.engineering.group@lexisnexisrisk.com. Before I end my talk, I'd like to extend my thanks and gratitude to my team members and also those team members who have moved on that have contributed to PyHPCC. You see my face as the face to PyHPCC, but there have been a lot more hands involved in bringing PyHPCC to the forefront and making it a reality. So I want a big shout out to my team for their hard work and effort. I also want to thank you for tuning into my session and for listening so intently. I will be available on the chat to answer any of your questions. So thank you and have a good day.